All right, let's get started here, everybody. Looks a little white. This quiz is due tonight then, right? So some of you put the answers in already? Yeah, do they all work? Because, you know, there might be one on there I accidentally have the wrong answer or something like that, or sometimes I put the wrong answer on purpose just to see if it's an answer that's just way whacked. There's no way it could be the right answer. And then all of a sudden I'll get some students that put that answer in, and there's only one way they're putting it in. I'm talking to somebody else that's already put theirs in, right? Okay, do you have any final questions on this baby? All right, so we're going to retire chapter 4. We get down to chapter 5 here. We got another test scheduled. So chapter 4, we'll retire that. The chapter 5 quiz, I just sent it out literally like 5 minutes ago. So here's the chapter 5 quiz. There's only 18 questions, but after every day, I'll tell you how many we can do. So there's a chapter 5 quiz in your email. Okay. All right. Chapter 5 looks like this then. And what chapter 5 does is, so we've done reactions. We can write formulas of compounds. We can calculate the stoichiometry of reactions, like if you want to produce so many grains of something, or we can add so many milliliters of something. But what chapter 5 does is it puts the heat into it, or the heat energy of reactions. So you can think of it this way. You have to split all of the reactant bonds, then you create new product bonds. If you get more energy out, now think about this. You got to put energy in to break reactant bonds. Then you form new product bonds. If you get more energy out into the product bonds than what you put in to break the reactant bonds, you get extra heat out, right? We say it is exothermic. If you have to put extra energy in to break the reactant bonds, more than what you get out when you make product bonds, we say the reaction is endothermic, and the net effect is you got to put extra energy in. So that's what we do, is we start calculating a little bit of heat. Now, how are you going to do that in lab? You're going to do that in water solutions, because all you have to do is measure the mass of your water solution and how much that heats up. It absorbs so many calories, or how much it cools down is so many calories. So we can do it in lab by measuring temperatures of solutions. So if we go way, way back, if we take this weighted object, and some of you have had some background in probably physics, where you would say the potential energy of this is mgh. That look familiar to some, right? Or once it starts moving, we would say that kinetic energy is 1/2 mv squared. I don't know if that brings back good memories or not. But what that does is it gives us the units of joules. This gives us the units of joules. So we know that these units, this mass would be in kilograms. The velocity would be in meters per second. So if you had a velocity squared, it would be meters squared over second squared. So 1 kilogram times meter squared over second squared is 1 joule. Heat energy in joules. Now, you are used to seeing the term calorie when you've done heat energy probably, and you look at food calories, and we'll talk about that a little bit. A lot of times you see this as a 4, and I think this book uses a 4. 4 or 6, I don't know what Owl uses, but sometimes I see a 4, sometimes I see a 6. So this right here is a conversion that you'll use quite a bit. Okay. So down here, we know that heat really is energy. And we know it goes from a hotter object to a colder object. And temperature is just a measure of the intensity of heat, not amount. Because a drop of boiling water versus a pot of boiling water, both have the same temperature but different heat content. Now, there's a question on the quiz right away. I think the question is, and I ask this all the time, what temperature does water freeze at? And we got to be concerned about that tonight, unfortunately. What temperature does water freeze at? In Celsius, it is 32. And in, oops, I said Celsius first, sorry. Celsius is 0, correct? And then we know that water boils at 212 and 100. So, do you want to make your spaghetti noodles faster? You're in a hurry to eat. So you decide that once the water starts boiling, I'm going to let it boil an extra 10 minutes before I put my noodles in. Because after 10 minutes, it's going to be hotter, right? Man says, no, water boils at 100, right? Doesn't matter if it's been boiling for 50 hours or 5 seconds, it's going to boil at 100 and your noodles aren't going to get any hotter, or your water is not going to get any hotter. So there's a question that relates to that on the quiz. Okay, so let's talk about system and surroundings. System is the object or collection of objects being studied. Typically, it's a beaker you're going to see on the next page. And if we have an open system, it's not closed up, you'll see that on the next page. And the surroundings is the rest of the universe outside the system. So here's our example. In the terms exothermic and endothermic. So if something is exothermic, and you can think about a beaker, and if this reaction here heats up, again, we're getting more heat energy out in making products than what we put in for heat energy to break up the reactant bonds. So if we're getting extra heat energy out, what is it going to do? Well, it should warm up the room a little bit, shouldn't it? So for exothermic, we say that the heat energy is less than 0. We know it's going to be negative. Versus if something is endothermic, Now, we're accelerating this greatly with a Bunsen burner, but if you just left this out without a burner in the room, the ice is going to melt, correct? And where is it going to get that heat energy from to melt the ice? From the room. So in that case, when we calculate heat, we are going to end up with a positive value. And in this case, the surroundings, you figure out your room temperature, the room has to put heat into the system, right? If we just think about a beaker and ice water here. Here, heat is going to go out of the system and into the surroundings. So summary again, endothermic, it absorbs heat. Heat flows from surroundings into the reaction. We need to add extra heat, and we know Q that we calculate is going to be greater than 0. If it's exothermic, it evolves heat. Heat flows from the reaction to the surroundings, and Q is going to be less than 0. Now, here's an I think I want to say this is the one from the book or from I don't remember. So if the reactants have some kind of energy right here, and then we form products here, this would be heat given off. And if it is exothermic, we know that heat is a product. And if it is endothermic, we got to put heat energy in. So heat is a reactant. Again, it takes more energy to break the reactant bonds than what you get back when you form the product bonds. Again, that's always the way to look at it. You have to break reactant bonds before you can form product bonds. And then the classic energy diagrams look like this. So here is an endothermic energy diagram. Here's the energy of the reactants. You have to put activation energy in to get everything split. But the net effect here is we have to add 100 kilojoules of energy. Now notice, here's our symbol that you're going to see. This little thing is called delta H. That's what you're going to see coming up. Again, endothermic, and in this case, exothermic. Okay. We often speak of heat as though it were a material that flows from one object to another. It is not. Rather, it is a form of energy. And the unit of heat, we're going to use calories or joules. A calorie is the amount of heat necessary to raise the temperature of 1 gram of water by 1 Celsius degree. That is the classic definition. Well, what about Kelvin temperature? If we go Celsius to Kelvin, we got to do what? We got to add 273, right? But if it goes up 1 degree Celsius, it also goes up 1 degree Kelvin. So sometimes you'll see Kelvin in here. All right. Don't be fooled. The calories on our food labels are really kilocalories. Or they call it capital C calories. The heat necessary to raise 1 kilogram, 1,000 grams of water by 1 Celsius degree. So the unit of heat is the joule, and we looked at that previously. If you really broke down the units, you get a kilogram times meter squared over second squared. And this is the conversion we'll use a lot. Okay. Sign convention. The amount of heat energy is Q. Heat energy typically and this is typically in kilojoules. It can be in kilojoules or calories. If Q is negative, if Q is less than 0, we know the reaction is exothermic. Heat is given off to the surroundings. Heat is a product. It goes on the right side. So if you see a negative value here, we know this has to go on the product side. And it goes on the product side as a positive number. And if it's greater than 0, we know the reaction is endothermic. Heat is added to the system from the surroundings. Heat is a reactant on the left side. Okay. Here is an owl example starting out. So the next page has an owl example. When 4 moles of iron rust to form iron 3 oxide, 1,648 kilojoules of energy is evolved according to the following equation. Now, you know those small heat packs that you buy that are in a plastic wrapper that are really cheap, right? Foot warmers, you can throw them in the bottom of your shoes or boots, and the hand warmers. Everybody knows what I'm talking about, right? This is the reaction. The reason they're dirt cheap and they're so cool is they're really environmentally friendly. All they are is sawdust, pretty much sawdust with iron, powdered iron. And the reaction is the iron is just rusting, forming iron oxide in there. And you get 4 good hours out of them, maybe 6, right? And they're dirt cheap. They're fantastic. They're absolutely great, other than and they don't get any oxygen to them because they're always sealed up in plastic. And as long as the plastic is still good, you can take them out years later and they should be fine. So they're a great reaction. And pretty much if you leave them outside, they're not bad for the environment or anything. So we get 1,648 kilojoules of energy is evolved. So when you see the word evolved here, you know that this is exothermic. And then the true value for Q would be a negative 1,648 kilojoules. So we know it's exothermic. What is the value of Q in the sign? Will energy go on the reactant side or the product side? And it for sure is going to be on the product side. And we could write a plus symbol in right here as 1,648 kilojoules. Okay, another odd question, I guess. When calcium carbide is manufactured according to the following reaction, 465 kilojoules of energy must be absorbed. So for this, then, we know that it is endothermic. And Q is going to be positive, so we leave it at 465. And it is plus 465, I guess, or 465. And it's going to go on the reactant side. Right, so that's now how it starts out. Not too bad, huh? Okay. Now let's talk about 5.2. In section 5.2, and I think this table came out of the textbook, I think. We actually have what's called a specific heat capacity or specific heat. And I use big C for this. Now, specific heat, and then I guess your textbook calls this big C with an SP here. And then there's a molar heat capacity if you have an entire mole of the substance. And then, as you saw in the gas laws, PV equals nRT, we use N for moles. I rarely am going to use this side at all. I don't think I'll use this side either, because you can always convert to moles. Now, if we look at this, and another thing, I'm not going to use Kelvin. Instead of Kelvin, I'm going to have degrees Celsius here. So this is the amount of heat you need to raise 1 gram, 1 degree Celsius. So for aluminum, it's 0.897. Iron, you only need 0.449. Copper will heat up faster. Gold will heat up even faster. Well, this is the big one right here, 4.184. If you want to heat up water, it takes a lot of heat energy. You put, and you're making your spaghetti now, you crank, especially if you have a gas stove, you're pouring heat to that to beat heck. And you've got 2 quarts of water on the stove, and you turn the heat on high, it takes a long time for that to boil, right? A long time. The fact that water specific heat is so high is what makes life on this planet possible. It takes a long time to heat up water. Otherwise, if it didn't have this high of a specific heat in the summertime, the lakes would heat up enough to kill all the fish, because the water temperature would get too hot, right? And the other way to look at this is, if you're trying to make ice cubes, it takes quite a while because you have to take away the heat as well. So the fact that water has this high specific heat makes life on planet Earth possible. Okay, now I'll bring it up when I get there. Here's a pretty good table of specific heat values. There's another problem. The specific heat values don't seem to be consistent out there. So if it's off by a little bit, it could throw the problem completely off. And there's an example of that coming up. Okay. So heat capacity definitions. The specific heat, I would just use capital C for this. Of a substance is the energy required to raise the temperature of 1 gram of the substance 1 degree. And that's 1 degree Celsius or Kelvin. And it's usually reported in joules per gram degree Celsius. So again, it will look like this: joules over grams times degrees Celsius is what it'll look like. But the multiplication down here is Okay, and again, specific heat means per gram. Molar specific heat, I don't think I'll uses that much either. But, you know, instead of a gram, you have a full mole. Okay. Now, you can represent the energy required to raise the temperature of any substance by this equation. Q is equal to MC delta T. Q is the energy in joules. It could be in calories. Or calories, depending upon your specific heat. C is specific heat and temperature change from T final to T initial. So how much heat is needed to warm 250 grams of water? So we know 250 grams is a mass, all right? From 22 degrees, about room temperature, to near its boiling point, 98. So then we know that this is T initial. I'll just put a TI for T initial. And then we know that this right here, of course, is T final. And the specific heat we're going to use is 4.184 joules per gram degree Celsius. So we can just put in Q is equal to MC delta T, and we should be able to just plug this baby in, huh? We've got 250 grams. And my specific heat, 4.184 joules. Look at me go now, look at me go. I'm going to put all my units in there. I'm going to put all my units in there. Joules per gram degree Celsius. Please, please, please put all your units in here. I still see people just put numbers in and then, oh, they've got a specific heat in kilojoules and they start out, it just doesn't work. Because your units are going to cancel out, right? So we're going to have 98 degrees Celsius minus 22 degrees Celsius for my temperature change. So when we get all done, grams, and my degrees Celsius here is going to cancel out. That tells me my answer is going to be in joules. So crank that into your calculator. What do we get? What do we really got? 2 sig figs, I guess. What do we get? Who's got? What do you got?
79,000.
All right, so 79,000 joules. Right? If you're on about 2 sig figs, is that 2 sig figs, right? Yeah, 79,000. You can report that as 79 kilojoules. I guess you could do this as 7.9 times 10 to the 4th if you have it in scientific notation on your calculator, depending on how it. But 79,000 joules, huh? Okay, let's do the next one here. The initial temperature of 344 grams of iron is 18.2. If the sample absorbs 2.25 kilojoules of energy as heat, what is the final temperature? So let's identify these here to be a better idea here. So my mass is 344 grams. And T initial here is 18.2. We are looking for T final. We know that Q is equal to, it's 2.25 kilojoules. Let's put it in joules, 2,250 joules. My specific heat of iron, I'll put Fe for iron, should be on the previous page. It is. So on the previous page, 0.449. Now, be careful because sometimes these are in kilojoules per, you don't know what unit unless you write them down and they should cancel out. So 0.449 joules per gram degrees Celsius. Okay, so we are going to have Q is equal to MC delta T. And let's see. I don't like to, I'm going to start putting these in, or we can solve it for T final, I guess. And I'll put them in. So we got 2250 joules equals 344 grams, 0.449. And this is going to go T final minus T initial, which is 18.2. If we solve this, we can take 2250 divided by 344 divided by 0.449, right? And if we do that, we're going to be left with 14.6. And that would have to be degrees Celsius equals T final minus 18.2. And we would end up with then, if we add 18.2 to both sides, 32.8 degrees Celsius. Okay. Here is a typical example as well. So I think this picture comes directly out of the book. So we're going to heat up iron, or excuse me, yeah, iron. 99.8, that should be up to the boiling point. So we can throw a chunk of iron in boiling water. At higher altitudes in Denver, Colorado, it's going to be a little bit less than this. We have room temperature water about 21, and this is not the best. You'd have to super insulate all of this, so you're not losing any heat to the surroundings. Then it says, it looks like the final temperature is 23.1. And that's going to be the final temperature of both, right? So we know that iron is going to lose heat energy because it goes from 99.8 down to 23.1. And we know the water is going to gain heat energy. Where's the water going to get the energy? From the heat of iron. So let's set this up. Now here's the key, and I'm going to put it in red. And you're going to see a way to do these problems. So we know that, I'm going to put this in red, the heat lost conservation of energy, and I'm going to split this here. Heat lost by the iron. I'm going to try to organize this pretty well. Is going to equal to heat gain by the water. So Q lost, Q gain, they have to be equal. So let's concentrate on the iron over here. And then these, this session, I'll put an equal sign right up here. Yes, these got to be equal. So for the iron, the mass of my iron is 80. Well, my problem doesn't, my example problem doesn't match my picture, but you get an idea. It's a different mass here. So it's 88.5 grams. The initial temperature, T initial of my iron is 78.8. Specific heat of iron is 0.449 joules per gram degree Celsius. The mass of my water is 244 grams. In my example problem, the initial temperature of the water is 18.8. And specific heat is 4.184. But for this problem, we're looking for T final. And it is going to be the same for both. It is going to be the same for both, right? Okay. So we're going to go Q lost equals Q gain. And what's going to lose heat is going to be my mass of my iron, specific heat of my iron, change in temperature of my iron, and gain is going to be my mass of water, specific heat of water, and change in temperature of the water. So let's plug in the numbers here. So we've got the mass of iron, 88.5 grams. 0.449 Now, here's the trick to these questions. If you don't write anything down today, write this down. You want to make the parenthesis change for your temperature positive. So we will interchange T final and T initial, whatever it takes to make a positive number. So my question to you is this: is iron that starts out at 78 that goes into 18.8 degree water, is it going to end up less than 78 or higher than 78? It's going to be less, right? It has to be less. So in this case, I'm not going T final minus T initial, or I'm going to get a negative number. We have to make this positive. So in this case right here, it's going to be 78.8 degrees Celsius, which is actually T initial, minus T final. Again, you have to make this temperature change. If you do not write anything down, write this down. This, if you make this positive, then it makes this way of solving everything so much easier. Because the textbook will put it'll be Q negative. It just doesn't make any sense. This makes life so much easier. Make the temperature change positive. So I don't have T final minus T initial, right? I have a negative temperature change, right? So this is really T initial minus T final. Make this positive. So if we go to the other side, the mass of water is 244 grams. My specific heat of my water, 4.184. And then my temperature change here, if I make this positive, it starts out at 18.8. I'm going to drop in there 78 degree iron. It's going to go up, right? So in order to make this positive, I'm going to go T final, which is going to be bigger than 18.8 that it started out. Again, you have to think this out and make this positive no matter what. Now it's just a matter of cranking it out and factoring out a T final here at the end. So this is going to take some crunching. So let's see what we've got here. Multiply, let's multiply these two, and that is going to be 39.73. I'm going to keep this in my calculator anyway, 65. 78.8. I know I've got my units right, minus T final. And these two here are going to be 1020 point. I've got way extra sig figs, but T final minus 18.8. Yeah, I could double check my units here, right? So now I can distribute this through. So if I distribute this through, I'm going to end up with 39.7365 times 7.8. I get 31.2362 minus 39.7365 T final. And if I distribute it through on this side, yes.
Isn't it 78.8?
Yeah, why do I have 7.8? Wow, that's terrible. Let's just, let's see if I can fix this up. 78.8, yeah. 78.8, yeah, it's terrible. 78.8. Then we're gonna end up with 1020.896 T final minus 19,192.8. I don't know why I kept all these numbers when I did this, but we're gonna add this to both sides. We're gonna add 19 to both sides, subtract 39, or my cheater's algebra is this. This is just what I say. I'm gonna put this on the other side of the equal sign and make it positive. I'm gonna change the sign. I'm gonna put this on the other side of the equal sign and make it positive, right? So if you do that, we are gonna end up with 22,324 equals 1060.6 T final. And then if we divide both sides, we end up with 21.0 degrees Celsius is T final. It ends up being quite a bit to crunch these, but again, when you do these in OWL, think of what's going to happen if you make the temperature changes positive. It just makes life so much easier. Okay. On the quiz, you could try 1 through 7. If you get a chance, 1 through 7 on this quiz, and we will continue here and do some calorimetry calculations next time. So don't forget, we got hours tonight, and so OWL chapter 4 part 2 and the quiz, right? All righty, have a great day. Hopefully you don't get snowed on.